Cool. Hello, everybody. So this is where we're at with the MIT humanoid at the moment. Still ironing out some bugs in the firmware. Still dealing a bit with state estimation. Has been a bit of a pain point, but we're starting to put it through the motions in the hardware. But unfortunately, these are all the real results I'll show today. About half the team is pushing on model-based control. I'm going to talk to you about the other half where we're pushing on data-driven, so learning-based control. So where are we with that? Well, in simulation works quite well. It's something we showed a couple weeks ago at TICRA. And this so far is all just pretty vanilla end-to-end deep reinforcement learning. But as a group, we're really moving away from end-to-end and towards modularized hierarchical motor control. So let me show you a little bit about just an overview of what we're doing in that direction. I think easiest is to understand this by couching it in what we understand well, so model-based approach. So we typically have this high-level reasoning over a long prediction horizon, but in a pretty static fashion. Then we have some intermediate level that starts to reason about the continuous time dynamics at a higher control frequency with a shorter, somewhat shorter prediction horizon. And finally, we have our whole body, like a low-level whole body controller that is operating at a high control frequency on the full state space of the robot, but without considering the future anymore, right? And we really think that this trade-off along the hierarchy of the prediction horizon and the resolution that we're actually reasoning at, both spatially and temporally, is not just a limitation, but actually a feature, and a really important feature of the hierarchy that we want to keep. So just kind of hypothetically, in what do we mean by this? Well, if I want to do this this behavior, like jump over this gap, I don't want to think about what is the exact trajectory that I need to take to jump this gap. I just want to think, I want to jump this, right? The problem with this is, well, that's a jump, and this is a jump, and that's a jump, and then you map all of these trajectories up into this high-level space. They should all map to a point, to different points that have a zero metric to this simple jump, right? So the inverse of that mapping is not well defined. This is where the horizon comes into play. We can disambiguate this by putting it into a sequence of like skill blocks to really see which of those trajectories do we actually want to use. And this kind of, and then we'll have at least one, probably just one intermediate level to help bridge this translation. And this is where we want to get to. We want to have a repertoire of little skill blocks that we can recombine in new ways and then purposefully learn new skill blocks when we want them. So there are, when we're approaching this from a bottom-up approach, so we're focusing really on level 3 and level 2 for now. There are 4 main pushes that we're focusing on. First is always just how do we design these reward functions? And here it's really how do we take a really task-specific high-level reward function and translate it into something that's dense and meaningful at the low level. And the work I showed you before from Safe One is not yet in the context of a hierarchy, but a step in that direction. Charles has been working on looking at how rich horizon we should have at rich level of abstraction. So this is related to what I mentioned to James before. For this, we're still using MPC because MPC as a tool really puts the prediction into the spotlight, so it's really the more appropriate tool for this question. We really think that as humans, we really make use of a sense of confidence. How confident am I that I can actually execute this? And this is something I talked about how we think we can do this last year. And then finally, we were looking at a lot of different ways of how can we actually learn these reduced order models. So in a nutshell, Hoje's been working on putting domain knowledge in the form of like capture points, things like this, into kind of a hand-tuned latent space for reinforcement learning. Jenny's been working on a dynamical latent representation in the form of decoupled oscillators for our mini cheetahs or quadruped to get emergence of natural-looking gaits. And the direction I'm really excited about is actually learning manifolds for these latent representations. And this has been spearheaded by Elijah and Chen Hao. I want to talk about this a little more in detail. So to give a little bit of context, a typical way that we would learn latent representations is with autoencoders. Basically how this works is you have some input, you compress this through your encoder to get your latent representation, you immediately decode this, and the advantage of this is that you can automatically label your input data. So you can use supervised learning instead of reinforcement learning, which is generally a lot more powerful. The catch for us is that in our setting, the input is some snippet of a trajectory. And so this loss ends up being an L2 loss, so a Euclidean distance between points along two trajectories. And this kind of metric is just not very good. It just doesn't really capture anything about the dynamics. So it gets hard to actually generalize outside of the data we've seen. There has been work trying to put more meaningful regularization terms directly into the loss. But what we think is actually a more promising path is something we found from the animation community, specifically this paper on periodic autoencoders. And the basic idea here is after you've encoded your latent embedding, they pass this through an FFT, so you get a parameterization of a bunch of sinusoids, and then your reconstructed encoding is now a function of time. So this is going to induce some manifold. And instead of trying to sample your latent space to get your trajectory, you can just predict this forward in time, and you can shape your trajectory smoothly by smoothly adjusting the manifold, by adjusting the parameters of this manifold. And we can use these predictions of where we think we should be in the latent space compared to a new encoding of the immediate past to get a more meaningful metric of how far are we from where we think we should be. This is kind of a visualization of how this is. Take a look at it after. It's all very much work in progress, but we found that we generally can extrapolate away from the data a bit better, and using those predictions is actually also really helpful. So, go for questions.
Yeah, so autoencoder, that's really static autoencoder.
Yeah, Joan will use a VAE or something like that.
So you're not using any conditional based on previous time steps or previous time?
You would get more fancy than this. Just to get the basic idea of how autoencoders work.
Because there's an advantage of that if you're doing the second order Markov process.
We're doing a temporal convolution as a first step.
Okay.
And then, yeah.
So those circle, are those directional units, or they're not represented?
No, the circle is just a representation of the sinusoids. So it's the amplitude, the frequency. Well, the frequency is not pictured, but the amplitude, and then the arrow is the
phase of the.
Yeah, this phase at time 0. Yeah.
I was wondering, are you using this like latent representation for like an estimation, or is it for control? And like, why do you need a reduced order sort of representation? Just for the uninitiated.
Sure. So I think one thing that's been kind of helpful for us about thinking about this is whether this is a control output or a prediction or a reference trajectory is just relative of which level you're in. So the output of one level is a prediction of where I want to be, and it's the reference trajectory for the next level.
Okay.
And then why we want to have reduced order models at all, to be able to plan long into the future, you can't really deal with all the details, and it's also just not important to deal with all those details. Right? So we want to be able to get to these fill blocks to be able to actually flip things around, explore different combinations, etc. So if you're like learning how to do parkour, when you're just learning it, you are going to think about, oh, I'm going to swing my leg like this, right? But after a while, you're just going to think, how am I going to deal with these obstacles? Well, I'm going to vault this, the first one, go into a front roll, and then jump off and do a pre or something like that, right? You can't really deal with that at the full resolution of your full state.
So
All right, I
in terms
will
of complexity, it's at some point it's too burdensome to reason about like a full discretized trajectory.
Yeah, both for the planning, but especially if you're trying to learn new things. For the exploration, it's really burdensome.
Okay, thank you.
Yeah.
Is the deployment on hardware difficulty related to your training? If so, do you want to talk about it a little?
Deployment on hardware of the learning stuff, we don't know yet because we haven't tried any of that. The current difficulties with hardware are mostly firmware bugs, like communication on the motor controllers. We've been having a bunch of problems with that, and then state estimation has been a big pain point.
Thank you.
We're going to test with model-based controls.
So what is your reinforcement learning? Is it some version of deep reinforcement learning?
Yeah, so for now we're just using pretty vanilla PPO.
Simulation. So
Pretty simple vanilla PPO and simulation using Isaac Gym. if that, okay. Oops.